looked into the procedure principle of mix design in the last lecture. Today we shall look into the Indian standard method of mix design. As I said, the mix design method is not unique because it is based on a lot of empirical experiences, empirical charts and graphs. Therefore, there are a number of methods, there is no unique method. Indian standard method is one of them, and that would be our topic of discussion today, and also we will take up an example problem. So, like all other methods as we discussed yesterday, Indian standard method also starts with determination of water cement ratio based on the strength. Of course, before that we have to find out target mean strength. So, step 1, yesterday we discussed what is target mean strength. Step 1 is to find out target mean strength, that is Fm, which is FCK plus 1.65. What is FCK? FCK is the characteristic strength, and that is the grade itself, right, because this is characteristic strength, this is characteristic strength, and this is the grade itself. Okay. So, we can follow it up. Now, the standard deviations must be determined at site, but when you have nothing available, you are starting for the first time, you do not know the degree of quality control, because we said yesterday that standard deviation is a function of degree of quality control you have. If you have better degree of quality control, standard deviation will be less, but if you have poorer degree of quality control, standard deviation will be higher. So, whatever it is, if you do not have a standard deviation value available, the IS 456-2000 gives you a kind of guideline. It suggests that in absence of any available data on standard deviation at the site, you can choose for for M10 to M15 a standard deviation of 3.5 MPa. For M20 to M25 grade of concrete 4 MPa, and above M30 up to 50, these are all we are discussing about normal strength concrete 5 MPa. So, this is the guideline given, but actually what should do is as quickly as possible, as soon as the data is available, one should determine the standard deviation from site data. The formula being given in the last lecture, one can just obtain, but you must have at least 30 sample data, 30 not 30 cubes, you should have 30 sample data, because 30 sample data is important, 30 sample data is important, because 30 is the one which will ensure 30 is the one which will ensure that you have actually 30 data will ensure that 30 data ensures 30 data ensures that you have statistically right number of samples. 30 data ensures that you have statistically right number of samples. So, that is why it is necessary to have 30 number of data. Right. So, this is what it is. Step 1 F is FCK is equals to 1.65 sigma. Step 2 is to determine water to cement ratio. Step 2 is to determine water to cement ratio, and that is what we do like this. You have a curve available from which you can determine water to cement ratio. Right. There are two sets of curves available. Let us look at these two curves. First curve would be something like this. First curve would look like something like this: water cement ratio versus 28 days compressive strength of cement, 28 days compressive strength of concrete. So, there is a single curve, and this represents a single curve for all the concretes, all the standard for all concretes made with all kind of Indian cements, basically based on empirical experimental data that was generated by doing lot of tests early in 70s, in 70s, and from that water cement ratio versus strength curve was determined. So, this is one curve. If you do not know what is the strength of the cement, you have a general curve you can use, and you can find out what is the strength of your concrete, 28-day strength of concrete, and using this data you can find out strength, water cement ratio based on strength. We will take up an example problem, it will be clear. So, when you have cement strength available, there is another set of curve given, 28-day strength of cement is available, you can use this set of curve, and this each curve represent a cement strength. For example, this curve A represent cement strength, 28-day cement strength from 31.9 to 36.8 megapascal, whereas this B represents curve B, which would be next curve, represents a cement strength of 36.8 to 41.7, and next one is 41.7, etc., etc., and the last one is 56.4 to 61.3. This is what is more important. First curve that we just discussed about is a curve which relates for all cements without distinguishing between cement strength. It just take all, for all types of concrete that is encountered in Indian condition. For that they have actually curves have been plotted between water cement ratio and 28 days compressive strength of cement. So, when 28 days compressive strength of cement is known to you, you can find out what is the water cement ratio. In this case, it is dependent on cement strength. Well, it is not necessary that all the mixed design procedure that is there, say a different mixed design procedure, they use cement strength as a basis for determination of strength, 28 days strength or relationship between 28 days compressive strength and water cement ratio. However, Indian code does it that way. In fact, other codes do not consider, because the graphs definitely ignore the effect of aggregate, etc., etc. Best thing is to do is find out the water cement ratio for set of strength versus water cement ratio curve for your concrete. That would be the best thing, but in absence of that, the code says that you can use these curves. So, if you know at least the cement strength or grade of cement, you can use that to find out what is the water cement ratio, because for corresponding to your target mean strength, first we find out the target mean strength, which we have said that is 1.65 sigma plus FCK. So, we know target mean strength from the formula that we have given earlier. Once this is known, using the target mean strength, I can come back and find out what is the water cement ratio required. So, this is the procedure adopted in step 2. Step 3 would be to determine water content, sand content for concretes, and this is done using a set of two tables actually, again based on empirical data generated. Now, let's recall our earlier discussion. We said the strength is mainly a function of water cement ratio, and in the mixed design procedure or principles that we have discussed in one of the previous classes, we said that water cement ratio is found out from standard deviation and the grade of concrete, which dictates the target mean strength, and also from durability. So, from durability consideration and from strength consideration, we determine the water cement ratio. Having determined the water cement ratio, we find out the water content from the maximum size of aggregate, the workability requirement, and shape of the aggregate, etc. So, here also in this particular IS method, what we do, first we have found out the water cement ratio from target mean strength from those curves, and the second step, first I have found out the target mean strength, second step I have found out the water cement ratio from the set of curves that I just gave you, and then now the third step we determine water content and sand content for concrete grades for two cases up to M35. There are two tables. Now, let us look at the first table. First table is something like that up to this M35 grade of concrete. This table is valid for M35 grade of concrete, and for different MSA, the water content required and the percentage of fine in the total aggregate, that is given. For example, for 10 mm MSA, 200 8 kg per meter cube of water is required, and 40% should be the fine aggregate in total aggregate. That means, in 100 of total aggregate there should be 40 fine aggregate, and if the MSA is 20, it is like this. So, it is a function of, as a function of MSA, we are finding out how much is the water required and how much is the fine aggregate required. But then we have not taken account of, we have only looked into MSA, we have not taken account of the workability, not looked into the fineness of the sand, not looked into the shape of the aggregate, etc. Now, this table is meant for specific conditions. I shall explain this specific condition later on, I mean just for the sake of introducing it now. This is meant for a concrete with water cement ratio of 0.6 with with crushed coarse aggregate, fine sand belonging to what is called zone 2 of Indian standard IS 383, because I mentioned that sands are classified in zone 1, zone 2, zone 3, zone 4 depending upon their grading. So, it corresponds to zone 2 sand and corresponds to a water cement ratio of 0.6. A compaction factor has been used as a measure of workability here, and this table corresponds to a compaction factor of 0.8 and crushed coarse aggregate, angular coarse aggregate. For other condition, an adjustment or corrections are given, and this table is valid only for concrete grade up to M35. A similar table is available for concrete grade more than M35, that is grade higher than M35, and this table is like this, you see. And you see that MSA does not, it is more than 20 millimeter does not exist, because when you have higher strength of higher grade of concrete or strength of the concrete required is more, you will have MSA will be smaller. You can't have 40 mm MSA with grades above 35, grades above 35, you can't have 40 mm MSA, and therefore, only up to 20 mm, and the basic starting water contents are given, and this is meant for a water cement ratio of 0.35 and same zone 2 sand, etc., etc. Then next step we look into a correction. Because water cement ratio will never be 0.35, it will be something else, nor it will be 0.6 for concrete grade below M35. So, you have to have correction factor for water cement ratio, correction factor for shape of the aggregate, correction factor for workability, because these are fixed for specific workability. Okay, next table we explain the same thing. So, two tables are given, table 4 and 5 in the code 10262, where you have for various MSA water required and that fine aggregate as a percentage of total aggregate is given, and then the condition for which they are given are like this, condition for which they are given are something like this. These conditions are, these tables are meant for crushed coarse aggregate, these are meant for crushed coarse aggregate, they are meant for fine aggregate zone 2, they are meant for water cement ratio 0.6 for first table, that is first table up to M35 grade table, and for 0.35 for grades more than M35, higher than M35. So, these tables are meant for fixed water cement ratio, fine aggregate and coarse aggregate. Anyway, what you do is you first find out, assuming that your aggregates are crushed aggregate is coarse aggregate is crushed, find your sands belongs to zone 2 and water cement ratio is 0.6 or 0.35 according to the table that you are using, and compaction factor of 0.8. For any other values of this, you need adjustment or corrections, and these adjustments are given in the next table. You see, these adjustments are given in the next table. For example, adjustments are given in change in water content. Now, water content is affected by, first of all, workability. So, if you have a compaction factor change, then there will be a change in water content. For higher compaction factor, you need more water. That is what we have seen, because compaction factor is nothing but it is a measure of the workability. This code uses compaction factor. Some other codes of course uses slump and VV test, etc., etc., but this our Indian standard code uses compaction factor. And the standard tables, those which are given starting tables, they are meant for a compaction factor of 0.8. If you have higher compaction factor, then you must add water. If you have lower compaction factor, then you must subtract water. So, water content delta W expressed in percentage, additional water or reduction in water, addition water or reduction in water, for each change in compaction factor 0.1, you need 3% change in water content. So, 0.8, supposing my compaction factor is 0.9, then I got to increase the water content by 3%. If it is 0.7, then I got to reduce the water content by 3%. Whatever is the value, you reduce by 3%. And of course, compaction factor does not have anything to do with the sand content in the total aggregate content as per this Codal requirement. Basically, the sand content would depend upon the packing characteristics of the aggregate system and packing characteristics of the aggregate system. So, the basic that you have found out for zone 2 sand, if you change your compaction factor, it is assumed that it is not changed at all. Okay, but shape of the aggregate is important, that would change straight away, that this delta W by 15 kg per meter cube, it will change this by 15 kg per meter cube. So, whatever is the water content you have found out, you reduce it by 15 kg, adjustment you do in delta W. So, these are not really, that is why it is not called correction factors adjustment, because this is in percentage, this straightforward in just kg per meter cube. Let us see how the sand would change. Now, sand zone 1, 2, 3, 2 for 2, this tables are meant for sand zone 2. Now, if you have zone 1, zone 3 or zone 4, if it is 1, then add the sand percentages by 1.5%. Now, zone 1 is coarser. Zone 1 is coarse sand. So, which means that you will have like for the maximum size in the sand is now more. You have more coarse material and then finer material. So, what you can do is you can, the amount of sand that you would be used can be reduced, should be increased, and if you have finer sand, then you can reduce down the amount of sand. Amount of sand you can reduce down if it is finer sand, because finer sand means for the same water content it would possibly need more water. So, finer sand they have reduced down in order to, since water content I am not changing with respect to this. So, finer sand it would reduce down, you should reduce the sand so that your water content remains same, workability remains same. It is also related to water cement ratio. When you have higher water cement ratio, you increase your water cement ratio, you got to increase the sand content. You got to increase the sand content by 1% for each increase of 0.05% in the water cement ratio. So, when you have higher water cement ratio, your sand content in the total aggregate system will increase, because we have kept the water content same. Now, if I have higher water cement ratio for a given water content, which means my cement will be higher, the paste is higher. So, if I increase the water cement ratio by 1%, if I increase by 0.5%, I increase my fine aggregate content also by that 1%, so that the paste can fill into the space that is available in the fine sand. Okay. Now, of course, water cement ratio has got no effect to the water. So, this is the correction factor, but this is by and large whether you understand from the theory or not, because there are so many factors there involved in the whole system, there are too many complicated interrelated factors, but these are based on empirical data generated and from that it has been found. And when you have rounded aggregate, your packing improves, so you need much less sand, and sand can be reduced by simply 7%. Sand can be reduced by 7% straight away, sand can be reduced by 7%. So, these are the adjustment that is suggested, adjustment suggested for water content and sand content in the mix. Now, having done that, now what we have done so far, we have first found out the water target mean strength, and correspondingly what is the water cement ratio. So, that is usually the step with almost all type of mix design. First you find out what is your mean strength, and correspondingly water cement ratio you decide, and this water cement ratio must satisfy the durability requirement. So, whichever water cement ratio is lower, you choose that water cement ratio. The next step is of course to try to find out the water content, in this case also the sand content. So, you find out the water content and sand content not directly, here you find out in 2 steps. First you find out the water content for 0.6 water cement ratio, 0.8 compaction factor for zone 2 sand and for crust coarse aggregate if your grade of concrete is lower than M35. For higher grades higher than M35, M40, M50 etc., what we do? We find out the water content and sand content for the condition that we have zone 2 sand, we have water cement ratio equals to 0.35, compaction factor 0.8 and we have crust coarse aggregate. And for various MSS we first find out the given MSS, we find out the water content. Then we are doing this correction or adjustment in the water content according to this table as just I have explained. So, by doing this I have now found out water content, I have found out the cement content and I have found out the percentage of sand in the total. So, then next what I can do, since I know the water cement ratio and I know the water content, I should be able to find out water cement ratio. First of all, first of all I must find out what is the correct water cement ratio, and this is found out as the minimum of water cement ratio from the curves that I have mentioned and the water cement ratio for durability, water cement ratio from durability. And then cement content then I find out, because I know the total water content now, this is known, water content is known to me now, water content is known to me, this W is known to me. Water cement ratio I have decided, one from the curve and from the durability, whichever is lower. So, that is why I written minimum. Since water cement ratio star is known to me, then W divided by water cement ratio, that would give me the cement content, that will give me the cement. So, that is the cement I require from considerations other than durability, and then I look into the cement content from the consideration of durability, whichever is higher I take that cement content, because durability gives you minimum cement content and this is the cement content I require from workability. So, the maximum of the 2 I take and that is the cement content, that is the cement content, right. So, that is the, so therefore, I have found out now cement content and water content, these 2 are known to me. Now, I must find out what is the fine aggregate content and coarse aggregate content. What is the fine aggregate content and coarse aggregate content? And you remember I said the volume is conserved. That means total volume of water, cement, sand and coarse aggregate must give me the total volume, sum total of volume of individual component must give me the total volume minus the air content if any, because our concretes are mostly not air entrained. So, volume of air that is present, because if you remember when we talked about compaction, we said that there will be some amount of voids which will remain, and this void should be of the order of around 1%, 2% and maximum 3%. So, not more than that, and this void content is again specified by the code. So, therefore, leaving this void content aside, rest of the space must be filled in by the sand, must be occupied by sand, that is the fine aggregate, the coarse aggregate, the cement and water. So, if I sum total, find out the sum total of volumes of individual component, they must add up to the total volume, because it is conserved. After all, each must occupy the spaces. That is what we talked about when we were talking about the principles of mixed design. So, what we are doing then here, we can see that what we are doing here is, you see, if this is my volume and this volume V can be written as 1 minus air volume, air volume, volume of air, 1 minus volume of air, A stands for air volume, this is air volume, that must be equals to the volume of water. Now, if W is the mass of water, 1000 kg per meter cube, it occupies, density of it is 1000 kg per meter cube. So, W divided by 1000, W divided by 1000 will give me, W is in kg per meter cube, So, W divided by 1000, W kg divided by 1000, that is the volume occupied by water in 1 meter cube of the overall concrete, right. And C divided by specific gravity of cement, which is usually taken as 3.15. So, C is the cement in kg divided by 3.15, that is the volume occupied by 3.15 divided by 1 by 1000, 3150, that is the volume occupied by the cement. So, this is the divided by 1000 occupied by the volume occupied by water, this is the volume occupied by the cement, and proportion of fine in total aggregates is known. So, fine aggregate total specific gravity, this is the volume occupied by the fine aggregate divided by the volume percentages occupied by sand in total, volumetric percentages, that was not mass percentage, volumetric percentage. So, this is the total volume occupied by all aggregates. So, volume occupied by aggregate is this, volume occupied by all aggregates are this, and P is the percentage volume occupied by sand in the overall volume of the total aggregate, as we have found out, volume occupied by fine aggregate. So, this is the total volume of the aggregate, this is the volume of the cement, this is the volume of the water, I mean all divided by 1 by 1000, that must be equals to the volume occupied by solid, total volume minus the volume of air. So, volume is conserved. So, because this solid and the water, they must occupy this volume, whatever is not occupied by air. So, I have an equation of this form. Now, when this is known, this value specific gravities are known, this is known, this can be found out, So, all this being known, I can find out this one. So, I can just find out this one, I can find out this one. So, when everything else is known, I can find out this one. These are known, specific gravity of fine aggregate will be known, P percentage you have calculated out. Similarly, I can have an expression for coarse aggregate as well. Only thing I got to do is, this portion of the total volume of the aggregate I can express in terms of the coarse aggregate volume, because coarse aggregate, this is the mass of the coarse aggregate, this is the specific gravity of the coarse aggregate. So, that is the volume occupied by coarse aggregate, and 1 minus P, that is the percentage occupied by the fine aggregate, that is the volume occupied by coarse aggregate. So, 1 minus volume fraction occupied by coarse aggregate. So, this divided by this will give me the total volume of the aggregate. So, therefore, this expression, again the same expression, only this has been replaced, and when all are known to me, I can find out this. So, uses these two equations, I can find out the FAGG, that is the mass of the fine aggregate and mass of the coarse aggregate in unit 1 meter cube of the concrete, because I can write this V equals to 1 minus volume occupied by air in 1 meter cube of concrete. So, if I know that, from that I can find out this. An example calculation will make, of course, the things better, it would make more understandable. Now, volume of air has been already given in the code. For example, if you have MSA is 10, for 10 MSA, for MSA equals to 10, the volume of air content is given as 3%, because the packing, it's finally depends upon what is the best packing you can attain. Now, larger the aggregate size MSA, you can attain much better packing. So, finally 3% after compaction, its approximate air content assumed is 3%, for 20 is assumed as 2%, for 40 is assumed as 1%. And as I said, V is given by this formula, V is given by 1 minus this air content. So, air content percentage is known, and so this will be simply, supposing it is 2%, 1 minus 0.2, B will be equals to, V is equals to, for 2% it will be 1 minus 0.02. So, this will be 0.98, this will be 0.98. So, I can find out V meter cube, that is 0.98 meter cube must be the volume of the all solids plus water, because air occupies 0.02 meter cube. So, that is how it is we find out. So, all proportions therefore, we can find out. So, all proportions therefore, we can find out. Let us take up an example problem. This will make IS method clear, because this is by and large this is a popular method in the country. So, therefore, let us look at an example calculation. Now, let us consider M25 grade of concrete, and we use a cement 43 grade, let us say, and also we assume that it is in moderate exposure, I have zone 3 sand that is available locally, and that is what I am using. Compaction factor is 0.9 I require. This is the compaction factor, because we have discussed how we arrive at these values from our requirement, from application, methods of placing, etc. So, my required compaction factor is 0.9, and I am going to use 20 mm MSA rounded aggregate, 20 mm MSA rounded aggregate, not crushed aggregate, rounded aggregate. So, this is the specification, and also I know the specific gravity of the cement is known, specific gravity of the coarse aggregate and fine aggregates are known. As and when they require, I will be using them to to explain through this example calculation the Indian standard method. Right. So, first step what we do, I said my grade is, first step is to find out the target mean strength. So, Fm is given as Fck plus 1.65 sigma, and if you remember, if you recall, I said that for M25 grade of concrete, M10 to 15 we use 3.5, sigma equals to 3.5 when nothing is available, and from 20 to 35 possibly we use 20 25 we use, or 20 to 30 we use 4, and above that we use 5 MPa. So, 4 MPa is the standard deviation given, my grade is M25, that is known to me. So, now I can find out what would be my target mean strength. Standard deviation is 4, grade is 25, then Fm will be given as target mean strength, Fm will be given as 25 plus 1.65 sigma, and if I calculate this out, this comes out to 31.6. So, I can take this as approximately as 32 MPa. So, that is my first step. First find out the target mean strength. We have discussed why we find out the why target mean strength is higher than the characteristic strength, and the formula we have also discussed earlier. So, first step is to find out the target mean strength. My target mean strength is 32 MPa. My step 2 would be to find out the water cement ratio. Step 2 would be to find out the water cement ratio, and that too I find out from curves. And I said my cement is 43 grade of cement, and this is the set of curves which I have discussed earlier. This is the set of curves which I have discussed earlier, right? Because if I did not know the cement strength, then of course I would have used one particular single curve which is there, and it will be very approximate. Oh well, it does not matter how approximate your mix design calculations are, because finally you have to do trial mix and you have to adjust. There is no other way. It is based on total empiricity, as I said. So, therefore, there is no other way you can get rid of trial mixes. So, you have to do a trial mix, only starting point you are getting. So, if strength of cement is not known, one could use that curve, which is a single curve encompassing all cement or all concrete that is available in this country, but that would be very, very approximate. Slightly better is this, that is I am now I know about the cement strength. So, if you remember, I said that cement's 28 day cement strength, for me it is 41.48, 41.7 to 46.6, because I said my cement strength is 43. If you remember, my cement strength I mentioned was 43 grade, and for 43 grade 43. So, 43 grade means 28 days strength of cement would be 43 here, and this belongs to this, and therefore, my curve would be C curve, my curve would be C curve, my curve would be C curve. So, therefore, I have selected C curve. Now, my target mean strength is 32. So, if my target mean strength is 32, that means somewhere here target mean strength, I should use this curve and find out the strength. I should use this curve and find out the strength, and that is what I do. You see, at 32 I draw a line and which cuts the C at this point, and then I just project it downward to get the water cement ratio somewhere there. I project it downward to get the water cement ratio there. So, I have now determined the water cement ratio, and you can see this water cement ratio is about 0.43. So, the water cement ratio is about 0.43. So, this is how I determine the water cement ratio. Target mean strength first I find out, and based on this, from this curve I find out what is the water cement ratio, right. Having found the water cement ratio, this is not the final water cement ratio, I must compare this with the water cement ratio specified according to the durability requirement, and whichever is lower I should select. Okay, we will do that exercise, we will do that exercise. Let us look at the next step. right. Next step is to look at the durability requirement. Now, you can see that durability requirement for my case it is moderate, we have stated it is moderate, and this is the row which I shall be using, moderate is the case, and this is the row which I shall be using actually. This row I shall be using, which has been colored actually blue for purpose of our discussion. And if I use this, then my cement content should be this, then my water cement ratio should be this, and my grade of concrete is M25. So, anyway we have chosen grade of concrete M25, that right in the beginning we have done, because we said it is moderate exposure. Had it been any other exposure, one had to choose the grade of concrete accordingly. So, my case it is this. So, water cement ratio therefore should be what? Minimum of minimum of this and 43. It should be minimum of this and 43, and my water cement ratio is this 0.43, because minimum of this 0.50 and 0.43. So, whichever is lower I take 0.43. So, 43 is my water cement ratio. Now, this water cement ratio star, that means it is finalized, this is available, this is final. So, that is how I find out my water cement ratio. Okay, let us see what is the next step. Next step is to find out my water content and find out my sand content, volumetric percentage of the sand content. And since my grade of concrete is M25, I am using this one, I am using up to M35 table, the table that was mentioned for up to M35, I am using that, and that table I have just reproduced, and I am using MSA 20. So, this is what I am using, MSA 20 MSA. So, if I use 20 MSA, my basic water content should be 186 kg per meter cube starting water, and volumetric percentage of fine aggregate in the total aggregate is 35%. So, I think this should be clear. The first I find out from, because it is below M35 grade of concrete. So, I just check what is my MSA, and in this case my MSA is 20, and with 20 MSA we just find out what is the water content to starting water content and what is the percentage, volume percentage of fine aggregate in the total. Having done that, we can now find out how much is the adjustment required. Okay. So, the adjustment is done in this manner, we had this table earlier, if you remember. So, delta W that is change in the water content, because there is a change in the zone, the adjustment required for the zone, because our the basic tables are meant for zone 2 sand. Now, our sand is zone 3 sand, and then the water cement ratio for the basic table is 0.6, our water cement ratio is different 0.43. So, there we will have some corrections here as well, and then we have compaction factor 0.9, whereas the table had the compaction factor 0.8, and our aggregate is rounded aggregate. So, therefore, we will have corrections in both delta W, that is water content, as well as the volumetric proportion of the fines, volumetric proportions of the fine. So, let us see this, as since our sand is zone 3 and we said that minus 1.5% for each zone, right, minus 1.5% for each zone. So, I will have minus 1.5 here, and then you see coming to compaction factor, and this will have no effect in the water. So, there is no effect here. Now, come to compaction factor, I had 0.9 compaction factor. So, compaction factor will have a correction or adjustment in water content alone, 0.9 minus 0.8 divided by 0.1, because for each 0.1 my correction is 3%. So, for 0.1 I have multiplied by 0.03. So, that is the multiplied by 186, that would be the correction, because 3% correction, 3% of 186. So, 3% of 186 is 3 divided by 100 multiplied by 186 into 0.1 into 0.9 minus 0.18. So, this will be the correction due to compaction factor change, the correction in water content, but no corrections here, no corrections in delta P. Then correction due to water cement ratio, there is no correction in this, only correction here, and how much is the correction? 1% plus and minus for each change of 0.05% of water cement ratio. So, my water cement ratio is 0.43. So, 0.43 minus 0.6, 0.6 is that that's corresponding to the basic table, and then adjustment for 0.43 I need. So, 0.43, since there is a reduction, so 0.43 minus 0.6, this will be a negative value multiplied by multiplied by 1 divided by 0.05, multiplied by 1 divided by 0.05, this would be 1, not 0.1, it is 1. So, there is no percentage I can write directly, this is 1 divided by 0.05 and minus 1.5 already I had. So, that would be, this would be the quantity. So, which would be something like something like 0.43 minus 0.6, which is equals to minus 717, minus 0.17, and divided by 0.05 would mean, divided by 0.05, for each 0.05 I have 1% correction. So, this would mean this will be equals to minus 3.67%. So, if you see, if you go back to, I had 1.5 minus 3.67 would make it minus, this is 7, 5.17. So, it will be something like 5.17, this is correct, this should be correct, yes, 3.2. So, 5, no, this is not 3 point, this would be 3.4, not 3.67, this is 3.4. So, 3.4 it would be 9, 4.9. So, this would be 4.9, corrected is minus 4.9, because this is 17 divided by 5 into 1 is 3.4 plus 1.5 will make it minus 4.9. Okay. So, 4.9 is a correction due to in this P, delta P, this is 4.9, if you see minus 1.5, and this comes out to be 3.4. So, makes it 4.9, that is what we have seen, and then additional correction will come because of the rounded aggregate. So, it will come minus 15 kg per meter cube here straight away, and here it will come 7%. So, 7 and 4.9 makes it 11.9, and here 15, and this one which we have added, because of the higher compaction factor you need more water. So, this gives us a net 9.2 kg per meter cube. So, correction in water, adjustment in water content is delta W is minus 9.2 kg per meter cube, and adjustment in the volumetric percentage of the fines is 11.9. Let me write it down here again. This is, you see, this has got two components, 186 multiplied by 0.083, 186 into 0.003, this is plus and minus 15. So, that makes it 9.2, and this is minus 1.5 plus 3.4 minus 7 minus 3.4, I mean this is minus, all are minus 3.4 makes it 4, and minus 7 would make it 11 minus 11.9. So, that is the adjustment. So, that is the adjustment, that's the adjustment. That is the adjustment in the overall adjustment, that is the overall adjustment in water cement ratio, I mean water content, and the volumetric percentage of the fine in total aggregate, volumetric percentage of the fines in total aggregate, right. So, now with these corrections we can look into change in the what total water content we can find out, and total fines we can find out. Okay, let us see. Now, water cement ratio, you remember that it should be minimum of the water cement ratio found out from the curve, that is this, and the one corresponding to durability. So, therefore, 0.43. So, water we found out to be 186 minus 9.2 now, the adjustment because of the rounded aggregate and because of compaction factor change, and this 9.2 if we subtract we get 177. Therefore, cement, now I can find out cement content, which will be maximum of the 177 the water content divided by 0.43 and 300, and which makes it 411.6 and is about 412 kg per meter cube. So, that is my cement content after all adjustment, and then I got to find out what should be my volume of fines and what should be my volume of fines and what should be my volumes of the coarse aggregate. What is the volume of fines and what should be my volume of coarse aggregate, right. Now, volume of fines, if I you remember, we said that we find it out from this equation, where this represents, this is the amount of water divided by 1000, obviously this is the amount of cement divided by specific gravity of cement, and 1000, because since I am finding out in 1 meter cube, I am taking the total volume as 1 meter cube, cement water in the kg per meter cube. So, everything I am finding out the quantity in 1 meter cube. So, in 1 meter cube, this will be the volume fraction of air, because we said there will be 2% air corresponding to our MSA 20. MSA 20 corresponds to 2% air content, 2% air content air, and therefore, this 2 I am subtracting from 1 meter cube. So, that must be the volume occupied by all the ingredients, namely water, the cement, the fine or total aggregate. This represents the total aggregate as we have seen earlier. Now, the volume of cement, volume of water is 177, because we know the density of water is 1000 kg per meter cube. So, if I had 177 kg of water, that would occupy in meter cube divided by 1000, 0.177. So, I just divide it by 1000. What would be the volume occupied by cement? 412 kg is the amount of cement divided by 3150, that is 3.15 the specific gravity, which is basically nothing but relative density with respect to water. So, 3.15 and 1000, right. So, if this had got a density of 1000, this will be 3.15 times 3.15 into 1000. So, divide this by 3.15. Now, fine aggregate, if fine aggregate mass is here, divided by P. Now, corrected P was 0.231. How does this 0.231 comes? We can see that. How does 0.231 comes? Okay, 231 would be coming like this. I had earlier 35, if you remember, I had 35 minus 11.9, and this 11.9 comes because 7% I can reduce because of the rounded aggregate, and I reduce 1.5% because of the zone of the sand, which is zone 3, and also I reduce 3.4% because of the change in the water cement ratio. So, considering all that, the total change was available minus 11.9 is the adjustment from 35, and that gives me 23.1%. So, my P is 23.1%. That means the volume fraction of fines in the total aggregate. So, volume of fines is fine aggregate, mass of the fine aggregate divided by the specific gravity of the fine aggregate. So, that is the volume of fine aggregate. If I divide this by 0.231, I get the total aggregate volume. So, total aggregate volume is this, is the total aggregate volume, this is the volume of the cement and this is the volume of the water. So, this sum total of the volume must, all of course divided by 1000 remains, must give me the volume occupied by everything other than air in 1 meter cube, and this is volume occupied by air. This is 1 is the total volume minus this. So, this is the volume occupied by all this material. So, this is the equation I use to find out the value of fine aggregate. Similarly, I can use slight change modification of this equation to find out the volume of the coarse aggregate, and here the coarse aggregate comes into picture divided by 2.6 and the volume fraction of the coarse aggregate, which is 1 minus 0.231, because this is the volume fraction of fine aggregate in the mix. 1 minus that will give me the volume fraction of the coarse aggregate in the aggregate mix. We said this is the proportion, volumetric proportion in total aggregate of fine aggregate in total aggregate, and this is therefore is the volumetric proportion of coarse aggregate in total aggregate. So, using these two equations, therefore, I can find out the quantity of fine and coarse aggregate I have, and I find out the quantity of fine aggregate as this and quantity of coarse aggregate is this, quantity of just making calculation like what I do, I 0.98 minus this quantity, which will comes out to be about 0.672 or something, 0.98 multiplied by 1000. So, actually 980, if you see, it will come out to be 980, it will come out to be 980 minus 177 minus minus 412 divided by 3000, 3303.15, and this is 672 point something, whatever it comes out, and if I calculate it, then I'll get if I calculate it, I get this, from these two equations I get 419.25 and 13.440, right, 44.0. So, now I can look into my total mixed design or mixed proportions that I have got. The mixed proportions, as I have got water, I have got 177 kg per meter cube, I have got cement as 412 kg per meter cube, fine aggregate as 419.25 kg per meter cube, coarse aggregate as 13.440 kg per meter cube. The sum total therefore would come to be 2352 kg per meter cube, and that is the density, wet density of the concrete. That is the wet density of the concrete that would be occupied in 1 meter cube of the volume. So, therefore, that is what gives me the total mixed design. Now, supposing I want to supposing I want to do further, I have to do actually trial mixes. I have to do trial mixes and I have to have some more adjustment. So, first thing I do is I do trial mix, but while doing trial mix, two things I need. I must actual water that I should add is that 177 plus the water present in the aggregate minus its absorption in aggregate in kg per meter cube. You see, aggregate, if it is dry, I mean some moisture might be present whenever I am using the aggregate. If it is of course in saturated surface dry condition, I do not have to add anything, it is 177 only, but actual moisture content could be more than that. So, if it is more, then that much water I should reduce down from total water, or whichever way, like it should be, actually it should be the added, there should be a correction for actual water present. If water present is high, water, it should be this should be minus actually water present. If it is higher than, if it is higher than, water present, if it is higher than water present is, if it is higher than saturated surface dry condition, that I must subtract. If it is less than saturated surface dry condition, that should be, that much water I should add extra, because that will go by inabsorption. So, therefore, that adjustment I will have to make. So, that is done by adding the extra amount of, first I find out how much is the moisture content minus the absorption, that much. If it is plus, then that should be subtracted, otherwise if it is minus, that should be actually, that should be that should be, if it is, this should be subtracted actually, not added, it should be algebraically subtracted. So, this is what I do, and then actual aggregate also, actual quantity of aggregate in the mix should be adjusted depending upon what is the moisture content in aggregate. If aggregate contains some amount of moisture, therefore, I should take a little bit of more aggregate, so that the moisture that is present, that additional weight, that is moisture weight, is subtracted from the total aggregate weight. So, this corrections are needed, extra due to moisture content, so aggregate content minus extra due to moisture content, and that due to absorption, that corrections are necessary. So, then do a trial mix and do final adjustment, then do a trial mix and then do a final adjustment. Now, this, therefore, moisture content at site has to be done. You do a trial mix, find out whether you are getting the right property or not. If you are not getting the strength, then if you are not getting the strength, then you have to reduce down the water cement ratio, and if you are getting the you are not getting the workability, you have to increase the water content, keeping the water cement ratio same. In case the first case, you must keep your water content same. So, that trial mixes, trial adjustments are required, and that is how we do the mix design. Thank you.